all back to our seminar for the last time of this year. Today our speaker is Cheryl Praeger from UWA. She will tell us about finite edge-transitive Cayley graphs, quotient graphs, and Frattini graphs.
Well, thank you, Sophia, for a beautiful introduction, a seasonal introduction. And thank you for the invitation to speak at this seminar. Can you hear me? Is it okay? Great. Thanks for helping me sort this one out. I am going to be talking about work that's really very, very new, but it goes back quite a time. There's two 19th century mathematicians whose names will occur, and I've got their pictures here, and they're, as I found out yesterday when I was preparing these slides, they were both born within a few years of each other in the 1820s. One is Arthur Cayley, who gives his name to Cayley graphs, and the other is Giovanni Frattini, after whom this Frattini subgroup is named, and that's going to appear as well. I'll be talking about symmetry of graphs, and I'd like to explain how, like the context of what I'm trying to do with making graph quotients. And so that'll be going back a little bit to some earlier work, and then mostly I'll be talking about work in the last 20 years. My collaborator on this work, his name is Behnam Khosravi from Iran. I've never met Behnam, but we've been working on this for the last 18 months, and I'll let you know about that. So it's really a reflection on finding useful graph quotients, and I'm particularly interested in graphs that are both edge-transitive and vertex-transitive. So the basic setup is that we'll be given, I'll think of them as finite for this lecture, finite graphs and simple and undirected graphs. So we'll just have a set of vertices and a set of edges. The edges will be unordered pairs of vertices. And we'll take a partition of the vertex set. So here's a silly picture of one. I've got three parts of my partition, and there's some vertices in each of the parts. And I'm going to construct the output quotient graph. The vertices of the quotient graph will be just the parts of the partition. So my quotient will have three vertices, and I will put an edge between two parts of the partition, two vertices, if there's at least one edge between vertexes in the relative parts. So I've got a path of length 3. I don't care if there's a lot of edges, I just put one edge in the quotient. And in fact, although this won't be relevant to the ones I'm looking at, if there is an edge within a part, I forget about it. I don't put a loop in the quotient, so that the output quotient is simple, undirected quotient graph. And the questions I'm looking at are, what symmetry properties of the original graph gamma could be guaranteed inherited by the quotient? And perhaps I would need to be a bit careful about the partition. So that's what I mean by quotient. There are some things which are easily guaranteed to be inherited. For example, connectivity. If the original graph is connected, then there will always be a path between any two vertices of the graph, and hence between any two parts of the partition. So the quotient is always connected. But to talk about inheriting symmetry properties, I want to mention an observation of Lotzi Babai back to 1985, which is essentially saying you must be very, very, very careful if you want to inherit any symmetry properties when you do this sort of quotienting of graphs. And so Babai's observation was really about two arc transitive graphs. So I'll briefly tell you what they are. So in a graph, we have two arcs, and these are ordered triples of vertices where the first vertex A is joined to the second B, the second vertex B is joined to the third C. The first and second are not equal vertices, so there's really three different vertices, and the first and the third might or might not be joined by an edge, I don't care, but anyway, that is a two arc. And the graph is two arc transitive if the automorphism group, so I'm going to say if the automorphism group is transitive on the two arcs and also transitive on vertices. So Lotzi Babai's observation was this in his paper in 1985. He said, you can choose your favorite regular graph sigma. By regular, I mean that every vertex is joined to a constant number of other vertices, so constant valency. Choose your favorite regular graph sigma. Then Lotzi will construct for you a two-arc transitive graph gamma, which has sigma as a quotient. And not just as a quotient, but the gamma will cover that quotient. And what that means is that in this quotient, the edges go really rather nicely between any two adjacent parts in the quotient. You will have a perfect matching. Every vertex in one of these two parts will be joined to exactly one in the adjacent part. And as most regular graphs have zero, have just the identity, the trivial automorphism group, it means that you would start out with a two-arc transitive graph with, that means quite a lot of symmetry. And then you could take, you'll find that it covers a graph which might have no automorphisms at all except the trivial automorphism. And so Lotzi learned from that, or believed that this was saying that two-arc transitive graphs were very wild. But for me, he's also saying you have to be very, very careful if you want a cover to inherit any of the symmetry of the original graph. So if we did want symmetry to be inherited, what do we have to do? So we might be starting with a subgroup of automorphisms of gamma. We might decide that we will only consider partitions which are invariant under that group. So by invariant, I mean that all the elements of the group are just permuting amongst themselves the parts of the partition. If we do that, then the quotient will admit the action of the group, perhaps not faithfully. So for example, if we started out with a group being transitive on vertices of the original graph, then G will be transitive on the parts of the partition and hence transitive on the vertices of the quotient. Also, if it's transitive on the original edge set, it will be acting transitively on the edges of the quotient. So that sort of guaranteed inheritance works. But it's not good enough. You don't get two-arc transitivity preserved. And it was my work in the 80s and 90s on trying to think, when could you possibly get two-arc transitivity preserved, that I realized that I needed to be taking an even more special example of a partition. So if I take the partition to be the set of orbits, vertex orbits of a normal subgroup N of the group G, then two-arc transitivity is preserved. You start off with a two-arc transitive graph on gamma, you end up with two-arc transitive graph on the quotient. And so I call these normal quotients because the partition is a set of orbits of a normal subgroup. Okay, so that was what I learned in the 90s. Today I'm talking about Cayley graphs. So what's going on for Cayley graphs? If we want to somehow or other take quotients of Cayley graphs and perhaps end up with them being Cayley graphs, maybe start off with edge-transitive Cayley graphs and end up with edge-transitive Cayley graphs, what kind of quotients are we therefore meant to look at? So first, let's define Cayley graphs with, well, we have the same definition. I define a Cayley graph, I start off with the group G and a subset of G called C, and my Cayley graph, I call it K of GC. The vertex set is G and the edges will be all of the pairs G, CG, where little g runs through the group elements, and little c runs through the elements of the joining set. So I want no loops, so the identity is not in C, because I don't want GG to be an edge. I want the graph to be undirected, so I want C to be closed under taking inverses. So for every C in capital C, also its inverse is in capital C. And I want connected graphs, and so a little argument says that this means I want C to be a generating set for capital G. So I'm interested in having inverse closed generating sets as my connection set C. Here's an example. Take the integers mod 5, so I've got 5 vertices, 0, 1, 2, 3, 4. C5 integers under addition. And I take the standard generating set 1 and its inverse -1 or 4, and I get the cycle. Okay, so that is a Cayley graph. Now, what kind of quotients? Oh, sorry, I'm not up to quotients, am I? I'm going to say what kinds of subgroups of automorphisms am I going to be interested in? So I want to consider, in fact, the what I'll call the affine symmetries of the Cayley graph. So here I've got my Cayley graph gamma, and the affine symmetries are going to be a product of two kinds of subgroups of automorphisms. The first I think of as translations. So that is the elements of the group G which act by right multiplication. And if I take a typical edge, it's G, CG, and that will get mapped to GX, CGX, and I guess that is an edge. So these are all automorphisms, giving me a copy, right multiplication, copy the translation group inside of the automorphism group. Of course, it's transitive on vertices. And the other part of the affine symmetry group is this AUT-GC. They are all the automorphisms of the group that lead C invariant. So little c under sigma stays inside the generating set C. And if I have that happening, then the natural action of sigma will send each edge, G, CG, to G sigma, and then because it's an automorphism, it's C sigma, G sigma, and that is an edge because the C sigma stays in C. So these are all automorphisms, and I'll get myself this extra subgroup of automorphisms of alt gamma. Quite nice, it's distinct from G. And so I'm thinking of this as a sort of affine subgroup of the automorphism group of gamma. It might be equal, it might be a proper subgroup. It's definitely vertex transitive. So if I take one of these Cayley graphs, see an inverse closed generating set, and I'm considering doing a quotient modulo some partition of the vertices, what are the nice partitions to take? Well, in my 1999 paper, I ran through this sort of thought process and realized that if I take P to be the right cosets of a, say, a proper subgroup H of G, that will guarantee that G still acts on the quotient. So same way as we define quotient before. The vertices will be all of the right cosets of this subgroup H. But it's not absolutely clear whether the quotient will be a Cayley graph. So next, if I said not just the right cosets of any old subgroup, but if I take a normal subgroup of G, then that will guarantee for me that the quotient is itself a Cayley graph relative to the group induced by G. So it's a Cayley graph for the quotient group G mod H, and it inherits the connection set HC mod H. So I get a Cayley graph. And if I put on one extra condition, well, sorry, a second extra condition, if I take a normal subgroup and it's also invariant under this ORT GC, then that will guarantee that the full affine symmetry group acts on the quotient. And all of these statements are kind of if and only if. So you'll get the affine group acting nicely if and only if I have the partition being cosets of a normal ORT G invariant subgroup H. Right. So these were things that I was looking at inside my 1999 paper, which actually was a paper I wrote for Bernard Neumann's 90th birthday. So in that paper, I was thinking about edge transitivity, and I called the Cayley graph normal edge transitive if this affine group of symmetries is acting edge transitively on the Cayley graph, because it seemed to me that this made edge transitivity very easily recognizable. Asking that the affine group is edge transitive is the same as saying that this automorphism subgroup, this ORT GC, which we know fixes the identity vertex, and therefore it's sort of acting on the elements of C which are joined to the identity. If I want AFGC to be edge transitive, then it would be nice if the ORT GC was transitive on C. That would actually give me arc transitivity, or it might be the case that ORT GC has exactly two orbits in C, a C naught and then the set of inverses of C naught, and that will give me edge transitive. Now, why was I interested in asking that the affine subgroup be edge transitive? Well, if I start off with a Cayley graph with this property, so the Cayley graph is normal edge transitive, and if I take a quotient relative to a normal or GC invariant subgroup H, then the quotient turns out also to be normal edge transitive. Now, of course, not all edge transitive Cayley graphs are normal edge transitive. You know, that's not the case, but you get a rather big, interesting family which are normal edge transitive. So the smallest counterexample would be ones of size 6. You could take the symmetric group S3 or cyclic group of order 6 and take the capital C, the joining set, to be all the non-identity elements, and that will give you a Cayley graph. It will be K6, and no matter whether you took the S3 or the Z6, it's not going to be normal edge transitive. So we don't get all of the edge transitive Cayley graphs, but we do get a lot of them. And so in my paper in 1999, there were many questions which were asked, and this is now 20 years ago. I asked if the normal edge transitive graphs could be perhaps classified for all groups in some interesting infinite family of groups. I asked questions about what was the difference between the affine symmetry group and the full symmetry group, whether that was particularly interesting. We could say interesting things about that. I also noticed that if you take the H, so you're going to form these quotients, if you take H to be normal and ORT GC invariant, so one of these good ones, but you take it maximal with respect to those properties, then the the quotient group will be characteristically simple. It'll be the product of certain number of copies of a simple group, either cyclic prime order or a non-abelian simple group. And so that the normal quotients you're coming up with will be normal edge-transitive Cayley graphs of characteristically simple groups. So these are sort of basic normal quotients, and every normal edge-transitive Cayley graph will have at least one of them, maybe several of them. So there were questions about whether these could be better understood. These special basic quotients could be better understood. And then how much information that would give you about the original normal edge-transitive Cayley graph. In particular, could you ever reconstruct the original Cayley graph from these basic normal quotients? And if you could, then how could you do it? And if you can't, then how much about the Cayley graph would you learn from the basic normal quotients? So they're the questions that I asked. It's now 20 years since then. So I'll talk a little bit about what's happened and then what this problem is that we've been looking at and what we found for it. So in those 20 years, there's been, I was surprised, 68 Math Science citations of this paper. And so you'd think maybe there's some answers to some of the questions, perhaps. And if I go through, and I went sort of breezing through some of these citations, most of them are addressing the question about the difference between the affine symmetry group, FGC, and the full automorphism group of the graph. Now, in my 1999 paper, I had shown that these two automorphism groups were equal in the special case where G was a non-abelian simple group and the Cayley graph was valency 3, so C had size 3. And this equality was taken up by a lot of people. So my colleague Mingyao Xu, with whom I was speaking in quite close correspondence at the time I was writing that paper, he decided to call Cayley graphs where the affine group is equal to the full group, he called them normal Cayley graphs because the group of translations was normal in the full automorphism group. And there's many, many, many papers about normal Cayley graphs, and often they just reference my paper as saying there are two concepts of normal and we're writing about this other one. Or they might have been talking about non-normal Cayley graphs, trying to explain why some Cayley graphs had special extra symmetries, and especially looking at simple groups. So there's quite a number of papers there. There's also a few papers which give you classifications of normal edge-transitive Cayley graphs for all groups in some families. Now, I'm just going to show you what those sorts of papers look at, and it probably indicates that this is quite a hard problem. So there are classifications of normal edge-transitive Cayley graphs for groups G, which are abelian and order product of 2 primes. Now, this was already done by one of my master's students before my paper was published, and I talk about it in my paper, so P times Q. There's a group of people that look at Frobenius groups of order 3 times the prime. Another of my master's students, Brian Kaur, and I published a classification of normal edge-transitive Cayley graphs of Frobenius groups of order product of 2 primes, PQ. There's a classification for non-abelian groups of order 4 times the prime, and for non-abelian groups of order 4 times the prime squared. So I think it's probably quite a hard problem to ask for these classifications, but why just these sorts of groups? I don't know. So that leaves the other questions, these sort of reconstruction questions. And I certainly hadn't thought much about these at all. So the question is, when can you reconstruct the normal edge-transitive Cayley graph from the basic normal quotient? And how could you do it? So this is where I heard from my colleague, Behnam, who wrote to me that he and his 2 brothers who are all, their names are all B. Khosravi. There's Behnam, Behnam, and Beirut. And they're interested in applications to use of Cayley graphs for modeling networks with optimal fault tolerance. And they were interested in having networks where you could sort of factorize the network, the graphs or the networks in some ways. So they were particularly interested in groups G, which had direct decomposition. So maybe N1 times N2 times NK. And they wanted to link the Cayley graph for G to something to do with the Cayley graphs for these normal quotients Cayley graphs. So the Cayley graph for C would sort of map onto the Cayley graph for NI and CI. And they took the strong product of these Cayley graphs for the factors and showed that you would get the original Cayley graph embedded as a certain kind of subgraph of the strong product. Anyway, this contact from Behnam led to a collaboration. I wasn't particularly interested in taking direct products of groups. I wanted to know what happened for groups in general. And so we started to think about the general question. So we've got a normal edge-transitive Cayley graph or group G, and we've got a collection of these basic normal quotients where we're factoring out by H, which is normal, or GC invariant, and the maximal sort of ones, so that the G mod H is a characteristically simple group. Now, separately for each H, and whether it's maximal or not, you can always consider the natural projection map from G to G mod H, which maps an element to the coset that it's contained in. And that will induce a graph homomorphism from the Cayley graph for G onto the quotient Cayley graph. Fine. So somehow or other, we would like to put together all of these quotient Cayley graphs in some way. We have to work out what way, to say something a bit more about the Cayley graph, the original Cayley graph. Now, group theoretically, you can sort of do it. You could take a direct product of these quotients and you could map an element of G to the tuple of cosets, HG1, HG2 down to HGK. That would still be a group homomorphism. But then we wanted to know, well, what does that tell you about the combinatorics? What, could that be a graph homomorphism of some nice description? Okay, so that were our questions. So let's look at the group thing first, because that turned out to me to be quite interesting. So we've got this group homomorphism. G goes to the H1G down to HKG, so the tuple of the cosets. It's a group homomorphism. The image is, it'll be a direct subgroup in the direct product of groups which are all characteristically simple. So maybe that's kind of interesting. But what is the kernel? Well, the kernel would be the intersection of all of these normal subgroups HI. For some reason that I will tell you about in the next slide, I'm going to call this phi of GC. What do we know about it? Well, each of the HI is normal, so this is going to be a normal subgroup. And so the G mod, it's the kernel of the map as well, right? So G mod phi GC is going to be this subdirect subgroup of this funny product of characteristically simple groups. The phi GC is normal, it's G invariant, because that's what all of the H's were. What other product? You know, what other properties does it have? And so because of these HI have got some sort of maximality associated with them, they're sort of relatively maximal subgroups, it reminded me of the Frattini subgroup of a group. Let me remind you or tell you what I mean by that. So the Frattini subgroup of a group G is defined to be the intersection of all the maximal subgroups of the group. And if I take the image of a maximal subgroup under an automorphism of G, it's again going to be a maximal subgroup. So you could collect together all the images of a given maximal subgroup and intersect them first, and that would give you an Aut G invariant H, which was maximal subject to being normal and Aut G invariant. So you could redefine the Frattini subgroup as being an intersection of H's, and these H's are all going to be all the maximal normal Aut G invariant subgroups of G. And if I go back, if I can go back, yes, the phi GC was the intersection of the HI over all of the normal subgroups, which are Aut G invariant and maximal with respect to that. So it seemed to be a little bit reminiscent of Frattini subgroups for a group. Now, the thing about Frattini subgroups is that there's this famous theorem that says that the Frattini subgroup is equal to the set of all non-generators of the group. And what do I mean by a non-generator? Well, an element is a non-generator if the following holds. So if I had a generating set X for G that contains little x, then I could remove X and I would still get a generating set. So this property is, the property of the element X is what we call being a non-generator. And the phi of G is equal to the set of non-generators for G. So we thought, well, is there some kind of relative non-generating property that's going to describe this phi G, right? So we've got our relative Frattini subgroup, and it's the intersection of all the HI, which maximal relative to being normal and invariant under this particular smaller subgroup of automorphisms of G. Okay, so we discovered that there was a sort of connection, and it depends on the concept of being what we call normal C closure. So what's that? If we take a subset X of G, it's normal C closure. So C is this thing that we're using to define our Cayley graph. The normal C closure we get by just throwing in all the images of elements of X under conjugation by elements of the group and images under automorphisms, which leads to the invariant. So we're expanding an X into its normal, because of conjugating by G, normal C closure. Here is what we found, that the phi GC, our relative Frattini subgroup, is equal to the set of all elements Y with a property which is a little bit like being a non-generator. Okay, here is this property. For any subset X of G, if the normal C closure of X union Y generates G, then also the normal C closure of X generates G. So in a way, these are like the relative non-generators. So we've got this funny kind of normal subgroup. It's got a definition in terms of intersections, and it's got a definition in terms of generation. So what do they look like, and does this fact help us to answer our question about reconstructing Cayley graphs? Okay, so what about the normal edge-transitive Cayley graph? Right, so we've already got our a particular quotient G mod phi GC, a subdirect subgroup of this product of quite nicer looking graph groups. the best thing we could hope for would be a description of this particular quotient, the phi is the phi GC, of the normal quotient where we just factor out by phi. You couldn't get anything better than that in terms of these basic normal quotients. So the question would be, do you get anything nice for this? And we've got these individual normal quotients, and we somehow want to put them together because we can multiply the groups, but what do we do with the graphs? And it turned out that the appropriate graph construction was the direct product. So I don't even know what people mean by direct product, so let me tell you what I'm going to mean by a direct product. If I've got a set of graphs, gamma I, simple undirected graphs, so vertex set VI, edge set EI, then their direct product is the graph with vertex set being the Cartesian product of vertex sets, and the edges, so x and y are both tuples, so x1 to xk and y1 to yk. So an xy would be an edge if and only if the ith components, xi, yi, are edges for each i. Okay, so the tiniest example would be this. We just had two graphs, and then each of them was just k2, one edge, two vertices, one edge. Gamma 1 cross gamma 2 just takes this cross thing here. So the 0 is joined to the 1 in the first, and the second coordinates in the 1, 0, 0, 1 joined here. So the direct product turned out to be the proper graph construction that we should be looking at. And what we proved is this. So here's our theorem. We start off with a normal edge transitive Cayley graph. So C is an inverse closed generating set. And we've got this relative Frattini subgroup that is associated with G and C. So first off, we might take all of them, but we take enough of these maximal, normal, OTC invariant subgroups H's, H1 to HK, so that we can get phi represented as the intersection of these H's. Given that, we will get a map. So we've already talked about taking an element of the group and mapping it to the tuple of cosets, H1G to HKG, and the phi was the kernel, so that induces a map from G mod phi into the direct product here. So we get a group epimorphism, so a group isomorphism onto a subgroup of this direct product. That's easy. What happens to the graphs? Well, I'm interested now in this particular quotient. You want to know, can we explain this quotient, the Cayley graph of G mod phi? Well, we get a graph isomorphism from this Cayley graph to what's called a full subdirect subgraph of the direct product of the basic normal quotients. Full subdirect subgroup means that we could project on each component and we will get a graph epimorphism, a graph homomorphism onto the basic normal quotient. So vertices go onto and edges go onto. So we get a full subdirect subgraph of this direct product. So in some sense, we're sort of reconstructing this amount of the Cayley graph. So that's the theory, and it looks like what on earth might it mean? So we thought we'd better look at what it tells us in one particular family of groups. How am I going for time? 5 minutes, yes, I can keep going a bit, but I won't go too much longer. So we decided to explore what all this meant for the family of dihedral groups, just to see what it was telling us. We discovered that if we took different inverse closed generating sets C, we would get different relative Frattini subgroups. And of course, they would be associated with different normal edge-transitive Cayley graphs. In the end, we ended up classifying all of the valency for normal edge-transitive Cayley graphs for dihedral groups. We didn't start out to do this, but on the way we found that there was a paper by Talibi, 2011, which had a conjecture about what these ought to be. And we ended up disproving this conjecture by finding a new family. So let me just show you a couple of technical slides, and I apologize for the technicalities, but we really did try to see what this would tell us. So if we take a dihedral group, so for me, a dihedral group D2n has got 2n elements. So it's got one element A of order, so an element, a generator of order n, an involution V that inverts A. The Frattini group, Frattini subgroup of G, is contained in this cyclic group of order n. Its generator is A to the m, where m is the product of the distinct prime divisors of n. So here's a couple of examples of inverse closed generating sets which give us normal edge-transitive Cayley graphs. We could take all of the non-central involutions. So the dihedral group is essentially got the group generated by A as an index 2 subgroup. And so this would be the non-trivial coset of that index 2 subgroup. And so that would give us a Cayley graph, which was the complete bipartite graph KNN. And if we take that inverse closed generating set, then the relative Frattini group is actually equal to the Frattini group, because this is preserved by all the automorphisms of G. So you can sometimes get the relative Frattini group equal to the full one. Perhaps a more normal inverse closed generating set for the dihedral group would just be to take a sort of adjacent pair of non-central involutions, so that the Cayley graph would be a cycle with its with the graph automorphism group being D2n. Oh, sorry, it should be. I better fix that one up. That's not quite true, is it? Anyway, we get a different sort of Cayley graph. The relative Frattini group turns out this time to be the cyclic group generated by A, which is always bigger than the Frattini group. And we notice for this class of groups, we can sometimes get the Frattini group to be trivial. And this would happen if A to the m was trivial. So that happens if and only if n is square free. And so we can sometimes get trivial Frattini subgroup. And in this case, if we go up to the first example here, the relative Frattini subgroup GC1 would be trivial. And our theory would be saying that in this case, we could reconstruct the full Cayley graph from all the set of basic normal quotients, and those basic normal quotients would, each of them, they would be complete bipartite graphs KPP for some of the primes P dividing n. So you can just occasionally reconstruct the whole thing. What did we find about these 4-valent examples? Well, there are actually 3 infinite families of normal edge-transitive 4-valent graphs for dihedral groups, and they have they're all isomorphic to one of 3 types of 4-element inverse closed generating sets. And the first 2 of these families had been discovered by Talibi, and he couldn't find any others, and so he conjectured that these would be the only ones. So with our theory, we started sort of looking at maybe originally we were trying to prove his conjecture, but we couldn't prove it, and we ended up constructing a 3rd infinite family. I haven't put in all of the extra congruence conditions that were needed here, but they're sufficient to show that any example arising from family 3 was not isomorphic to, or could not be obtained from families 1 or 2, and that this was this contained infinitely many examples. So so we went that far. We developed some theory. We tried it out on one infinite family of examples. And here are some of my Christmas wishes. It would be lovely to know a bit more about relative Frattini subgroups for other families of groups G. Like, how are they related to the Frattini subgroup itself? How do they change if you change the inverse closed connection set? You need sort of nice ones to get normal edge-transitive graphs. And then it would, if you knew a bit about them for other families, it would be nice to explore the normal edge-transitive Cayley graphs to know what kind of basic normal quotients you would get, and what kinds of subdirect product graphs you get, what, you know, how much you can retrieve about the full normal edge-transitive Cayley graph. So thank you, everyone. Happy Christmas, and please stay safe.
Thank you, Cheryl. So to start, you have a comment in the chat from Eric. You can just read it yourself.
Not serious.
Yes.
But then, do we have any questions? Okay, so I will start maybe then. Yeah, you talk about these relations, like wanting to know more about the relations between the relative Frattini subgroup and the Frattini subgroup. I might have missed this, but do you know, like, is there anything you can say in general? There's no like containment each, like, either way, or
yeah, so always always the Frattini subgroup is contained in the relative Frattini subgroup.
Okay.
Yeah, and we didn't have many examples, so sometimes it can be equal. It seemed like typically it wouldn't be equal.
Okay. And then so what exactly is it that happens when the Frattini subgroup, or when they both are trivial, I guess?
If they're both trivial, then this kind of canonical quotient is actually the whole original Cayley graph. And so in the case where the phi is trivial, this theorem would be saying that the original Cayley graph was actually some particular kind of subgraph of a direct product of much simpler graphs, so graphs that characteristically simple groups. And so maybe you have a genuine combinatorial construction of the normal edge-transitive Cayley graphs in terms of Cayley graphs for products of simple groups, you know, products of isomorphic simple groups. And so maybe it's even more interesting to understand what these are. What are the possibilities to get transitive Cayley graphs there? I was actually really surprised that we managed to prove this.
Yeah.
And I'm very surprised at the at what this group turned out to be, but it did seem to have some interesting group theoretic characterization, which in fact we used that non-generative thing. We actually used that when we were exploring the dihedral group. So it wasn't just vanity, group theoretic vanity at finding out a nice a nice property of the group, but it was kind of useful.
Yeah. Okay. Yeah, but I guess like with this theorem, you kind of want to know when these groups are the same, when these subgroups are the same. That would be nice.
It would be nice if there was a family of groups with trivial Frattini subgroups, so that's probably easier to get at. But then we still don't know if the Frattini subgroup is the same, because these relative ones which we care about for the graph, they could be much bigger. Yeah. So it would be nice to know when these guys, with these relative ones, would be trivial. And I don't know lots of examples of that.
Yeah, I see. Do we have other questions? Sorry?
Yeah. I would love it if someone wanted to explore this for something other than the dihedral groups, just to figure out what on earth's going on.
Yeah. Yeah.
I'd like to ask, I forget what it was called, but the closure you were using to define the relative Frattini subgroup. I was wondering...
For that theorem, yeah. Yes, here.
Yeah, so this normal C closure, did that come up elsewhere in any of this theory, or did you guys make this up to capture this notion? Or
we made it up because we wanted to know if there was some characterization of this subgroup which was like the characterization of the Frattini subgroup, and also we needed this property to prove the combinatorial theory about the Cayley graphs. I don't know if there's anything simpler. It would be nice if there was something simpler than this. But this is definitely well, we believe this is a true theorem, it's a true characterization, but whether there's a simpler characterization, I don't know. You notice that it's for the Frattini group, of course, the intersection under all the automorphisms, that's going to be a characteristic subgroup and automatically normal. But when we go to the relative case, where we're only interested in automorphisms that leave C invariant, being G C invariant certainly doesn't tell you that the group is normal. So we have to put that in as an extra condition. And we need to look at the normal subgroup so that we can get a nice graph quotient. So it's all a bit kind of natural, but a little bit different.
Yeah, it seems the conclusion seems to like make the definition, like it seems to validate the definition, right? It seems like you've got the right kind of theorem, so it seems like the right kind of definition. It's just bizarre at first sight, I guess.
Yeah, it is. I suppose we could say it's a set of all y such that whenever a normal C-closed generating set contains y, you can throw y out. But